Hey guys, this is Romit, the Actuarial guy. Today, we start up with the curriculum of subject CD5. This is the first lecture for the subject. Yesterday I had uploaded my introductory video on subject CD5 and I got a few reviews, a lot of comments, and thank you for that. Some people pointed it out to me that my handwriting in the video was quite unreadable and it was not good. So from this video on, I have decided to make it a bit more systematic and improve on that. Keep giving me a review so that I can improve on the content as well as the presentation. I hope you enjoy this video, and now I am going to start talking about the subject. So here in this lecture I am going to cover the basics of life insurance mathematics, that is covered in chapter 1, 2 and 3, and I'm gonna be discussing a few topics out of these chapters, not in a particular order, because I believe that there should be a bit of a different order for discussing these things. So I'm gonna make up my order for discussing these things, and I will be taking the entire content of these these three chapters in this video and the coming one. So here I am going to start by introducing chapter number 1, life assurance contracts. So this is chapter number 1. So first of all, what do we mean by a life assurance contract? The first thing we have to discuss here is what is the difference between insurance and assurance. This is a very basic thing. Most people fail to understand that there is a difference between insurance and assurance. So when I start talking about insurance in general, there is a clause in every insurance contract that is called as indemnity clause. What this means is that the insurer promises to the insured to make good any loss that is suffered by them, which is covered by the contract. So for example, if you get a car insurance or you get a fire insurance on your house, whenever there will be any loss by fire to your house, the insurance company will pay you a certain amount with which you can get your house recovered, and after such a payment is made, your loss is made good and you are no more a party at loss. But with life insurance contracts, or rather I should say life assurance contracts, there is an involvement of death. The company cannot make good the loss of life. They cannot bring the person back. Instead, what they do is they assure you a certain sum, a certain amount. So that is the difference between a life insurance and an assurance contract. And a life insurance contract is always that of assurance, technically speaking, and never of insurance, because they can never bring back a person who is dead. Okay, so that is the idea behind this entire thing. Okay, moving on to the topics in this chapter, I will be discussing the types of life insurance contracts, types of life assurance contracts. So there can be many life products, but there are four basic kinds of contracts discussed in the core reading. They are on these bases. Okay, so if a life assurance contract is made, there can be a payment on death of an individual or on survival to a particular date. Okay, so, for example, under such a contract, the company says that if a person dies within the next 10 years, the insurance company will pay a sum of, let's say, rupees 1 million. And under such a contract, the insurance company says that if a person dies over the period of next if the person survives the period of next 10 years, and if they do, the insurance company at the end of the 10 years would be liable to pay them an amount. And there are contracts made with a combination of these two elements. Okay, so there are four types of contracts on these bases. The first contract is called as term assurance. Term assurance. Okay, so what a term assurance is, that a insurance company promises to pay the policy holder a certain amount of money if the policy holder dies during a particular period, let's say 10 years. If a policy holder dies during 10 years, the insurance company will promise to pay them amount of 1 million, and this is an example of a term assurance contract, and it is very easy to understand. If I get to the second type of contract, it is a whole life assurance. Whole life assurance. What a whole life assurance is that this clause of 10 years, this part, it is not here, it is not present. Only the contract is that whenever a person dies, the life insurance company would be paying him an amount of, let's say, rupees, the pounds 1 million whenever he dies. So a whole life assurance is a term assurance without any time limit. The third type of contracts are called as endowment contracts. Endowments. Now these are made out of the survival benefits. The company says that if a person survives for a period of 10 years, that is an example, the insurance company would be liable to pay them 1 million pounds. And the fourth type of contracts are called as endowment assurances. But this means that it has an element of both endowment and assurance. Both are included here. So this is basically a combination of a term assurance and an endowment contract. When both of these are combined, we get an endowment assurance. So what this says is, there are two clauses, okay, in this. If a person dies during the next 10 years, there will be a payment of 1 million pounds. And if this payment would be made on death, whenever the person dies. If he dies in the first year, the payment would be in the first year. If he dies in the second year, the payment would be in the second year, and so on and so forth. And if he survives to the end of the term, that is 10 years, of course, there will be a payment on maturity. Maturity is the point where these 10 years expire. So after 10 years there will be a fixed payment if the person survives. So these are the 4 kinds of assurance contracts, and we will learn about their valuation and everything eventually, but this was just a basic introduction. Okay, so the next thing we have to discuss now is from chapter number 2, life annuity contracts. We will get back to chapter number 1 again when we will be discussing the mathematics of life assurance contracts. For now, I will give you an overview of the chapter number 2, life annuity contracts, without discussing any mathematics. This is an introduction to the types of contracts. So what is an annuity? From subject CD1, we remember that annuity is a series of payments. Right? In subject CD1, these series of payments were made by one party to another. These example of these were loan installments, and there were income schemes paying perpetual amounts in exchange of a single lump sum payment, and that was the deal with CD1. But in subject CD5, life annuity contract is dependent upon life again. So there are probabilities involved here in these annuities. There will be a perpetual stream of payment provided that a particular life is alive. So that is the condition with these annuity contracts for the purpose of this chapter, if we talk about. So first type is a whole life annuity. A whole life annuity. What this means is that till a person is alive, he is going to receive an amount from the life assurance company, and it would be a perpetual amount which will keep on going till he is alive. Okay, the second type is a temporary annuity. Okay, a temporary annuity is one in which the payments are made till a person is alive, but they are limited by a term. For example, I am a life insurance company. I tell my policy holder that I will make you payments of rupees 5,000 per month, not rupees, pounds 5,000 per month till you are alive, but it would be limited by 5 years. So the life insurance company would make payments till the person dies or till the expiry of 5 years, whichever is earlier. So there is a whichever is earlier sort of a clause here. So minimum of death or 5 years, the expiry of 5 years, the payment would be made till this time, the minimum of death or 5 years. So if death comes before 5 years, the payments would be till death, and if he survives for the next 5 years, the payments would be for only 5 years. Okay, so that is the deal with temporary annuities. Third type of annuity is a guaranteed annuity. This is just the opposite of temporary annuity. I'll tell you how it is the opposite. Under a guaranteed annuity, the payments are guaranteed for a fixed term. Guaranteed for a fixed term and dependent on survival thereafter. So let's say the example, I'll be giving the example here. So for a guaranteed annuity, I will tell the policy holder that I'm the life insurance company, and I'm telling the policy holder that I will pay you £5,000 per month for a period of 2 years guaranteed, and thereafter till you survive, till survival. So the element here is that the payment should be maximum of 2 years or survival. If the person survives for 2 years, then he will be paid till survival. But if he dies before the expiry of 2 years, he will be getting the payments at least for 2 years. I'm sorry, it is not maximum of 2 years in survival, it is the maximum of 2 years and the time of death. I'm very sorry about this. Okay. So maximum of 2 years or death. So if he dies before the period of 2 years, he will be getting payments for 2 years, and if he dies after 2 years, he will be getting these payments till his death, because then death would come after 2 years and it would be more than the 2 years. So he gets the payment till the maximum of these two. So these are the three kinds of annuities. That was almost it for the introduction of contracts for now. Now I will be discussing the mathematics here, the mathematics of these contracts. Okay, so that is what I'm beginning with, and I will firstly start by introducing what prerequisite knowledge do you need here from subject CD1 and CD3. I had explained how CD5 is dependent on subject CD1 and CD3, but now I will be discussing the mathematical formulas that you would need here from subject CD1 and CD3, so that you know if you have if you have forgotten those formulas, or you have not studied subject CD1 or CD3 so far, you can just recall them. But I would not suggest you to take up subject CD5 unless you have at least studied subject CD1. So here we go with the basic formulas. So I will title these as prerequisite formulas. First of all, prerequisite formulas for mulas. Okay, so that is what we are discussing right now. So first of all, talking about CD1 formulas. CD1, we had something called as discounting. So we used to calculate present values there. So the formula for a present value was the amount, whatever the amount of payment is, or the cash flow is, multiplied by the discounting factor, which was V to the power of n. And this V to the power of n was nothing but simply V to the power n was 1 plus I, the interest added to 1 to the power of minus n. So this was just a sort of a formula which helped us remove interest out of these amounts and take them to past. Similarly, accumulated value or AV was amount into V to the power of minus n, or I can write this as amount into 1 plus I to the power of n. So this was what subject CD1 taught us about PVs and AVs, and this is what we will be using here. Next thing which was discussed in subject CD1 was an annuity regular. The formula for the present value of an annuity regular was something like this. It was 1 minus v to the power of n upon I, or if I write it more in detail, it would be 1 upon 1 plus I to the power of minus n divided by I. Okay, so this was the formula. If I talk about annuity dues, these were the annuities payable at the beginning of the terms. So if I talk about these annual annuity dues which were payable at the beginning of the year, if I need the present value of these things, it is the same as this, just this I changes to a D, because we would need to discount them once more. So we can derive these formulas using GP. If you want me to discuss the derivation of these formulas, you can just comment and tell me to discuss the derivation of these formulas, but since it was covered in subject CD1, I won't be discussing the derivations here. If I talk about a continuous annuity from subject CD1, the formula was 1 minus V n upon delta, which was the force of interest. So again, this was the formula. If I talk about annuities which were payable for more than once a year, they were denoted by this sign. This was the number of payments. Let me call it M, and this is N. So if an annuity was payable more than once a year, the formula used to change a bit. It was 1 minus V n divided by IM, where IM is the nominal rate of interest. So this is basically denoting that if interest is charged on the payment M times a year, then this is the annualized rate. Okay, so this is the annualized rate. If you want me to discuss it again, just ask me in the comments below. Okay, so this was the deal with CD1, and these are the formulas which are required here. This was all about the CD1 part, and if I talk, it's hard to draw a line with these things. Okay, so if I talk about subject CD3, the prerequisite knowledge here is very simple, and you would have learned these in your school too. So I am just discussing these here. Expectations or mean. Formula for mean from subject CD3 was nothing but we used to multiply. If I talk about a discrete random variable, we used to multiply the values with the probabilities and add them over all the values of x. So it was sigma x px summed over all the values of x. If I talk about a continuous series, it was integration, because this is just the continuous version of summation x fx, again the probability, and dx. So this is something you need from subject CD3. If I talk about the variance, which is a measure of spread, so if I talk about the variance of x, it is nothing but expectation of x square minus expectation of x whole squared. Again, this is very simple and very intuitive. There is a logic behind this formula, and I just might make a video on it someday. And if I talk about standard deviation of x, it is nothing but the under root of variance. So these are probably all the things you need to know out of subject CD1 and subject CD3, and that is all the content. So this is what you need from subject CD1 and CD3 in order to understand subject CD5 in detail. Now I did not discuss the derivation for all the formulas, but my approach for subject CD5 would be to discuss all the derivations that have been described in the core reading, and I will make you understand all the derivations. And where we cannot do the derivations, they are too high order, we will try to understand the intuitive logic behind these things. Subject CD5, it is just about reading the mathematics. What I mean by that is that you need to translate your contract terms. You need to translate your contract terms and write it in a mathematical fashion and solve it. And that is what we need to learn, to read and write these contract terms in a mathematical fashion. And that is what makes this subject very interesting, that it is very practical and it is directly applied by insurance companies. Okay, so that is the deal with subject CD5. Now moving on to the content of subject CD5 again. I will first of all discuss a few assumptions. I will change the color of my pen here. I think you like it. Red is good. Okay. So I will discuss a few assumptions of the contracts under CD5. So the first assumption that I would like to discuss is that under all the contracts in CD5 which we are going to discuss, the amounts payable by the insurance company are known in advance. What do I mean by this? What I mean by this is that when the insurance company and the insured make a contract between both of them, the amount is pre-decided. Whatever the amount of claim is, it is pre-decided. There can be such contracts where the amount is not pre-decided and it is an uncertain amount, and it might be a random variable with its own distribution. But here we will not be taking that. The amount would be fixed. There is a fixed amount, and if you want to know more about the amounts which are not fixed and they are not known in advance and they are random variables, that is discussed in the ST subjects. So if you take up life insurance in ST subjects, you will get to know that. Okay, and the second assumption is that the interest rate is also known as in advance. That is, interest rate is deterministic. Now we all know that the interest rate in an economy keeps on changing, but here for the subject of sake of subject CD5, we will assume it to be constant over years and known in advance. In subject CD1 we had discussed stochastic interest rates, which was interest rates which was chapter 14 of CD1, but we will not be taking these into account here. This will only be a discussion of deterministic interest rates. Okay, so that is what the assumptions of this subject are. Now I will move on to the mathematics of this subject. So in order to discuss the mathematics of this subject, the first thing we need to know is that the expected present value, which is a very important concept in subject CD5, this is if I talk about a discrete random variable, nothing but amounts, sum of amounts into the discounting factor and the probabilities. And these are the first principles. Every actuarial subject has some basics called as the first principles. So these are the first principles of subject CD5, and that is the deal with this subject. This is the key to deriving all the formulas of this subject. So first thing, we already know about the amounts. Amounts are fixed and they are going to be given in the questions. The discounting factors will again depend on the interest rate, which is deterministic. So far we haven't talked about the probabilities, and this is something I would like to talk to you about now. So these probabilities, they are covered in the chapter number 3 of this subject called as life table. So life tables is chapter number 3 of subject CD5, which covers the probabilities relating to this and how do we calculate them, what are the symbols that we use. So I am going to talk about these things right now. First thing that I'm going to discuss are notations, some important notations which you must know and their meanings. So let's start with this. We know that if I talk about probabilities in case of a life assurance contract or a life annuity contract, they can be of two types. They can be for death or they can be for survival. So the probability for death as would be denoted by a symbol Q, and there is a X here and a T here. So this is read as TQX, which means that a person, this is the probability of a person aged X dying within the next T years. As opposed to this, the probability for survival is obviously denoted by a P with the X and a T here, and again this is the age of the person and this is the term for which we are talking about. So this is the probability that a person aged X dies within T years, and this is the probability that a person aged X survives for at least another T years. And as you would expect, the sum of these two probabilities would be equal to 1. So this is something we must know. So how do we calculate these values? To calculate these values, these symbols, the value of these symbols, we would need to introduce another very important and a fundamental quantity, that is mu x, or the force of mortality. So force of mortality is similar to a concept that you must remember from subject CD1. What force of mortality basically means is this is the number of people that we expect would die in a very, very small, infinitely people dying in an infinitely small period of time, and this quantity can be computed through a lot of measures that are discussed in subject CD4. As I discussed earlier too, mu is a subject CD4 concept, and we discussed the calculation of mu in subject CD4. Here in subject CD5 we will learn to use the value of mu in order to calculate these probabilities, to calculate the value of the premiums and the reserves and all that. So this is an application of mu x. So now I will discuss with you how do we get from mu x to px, that is tpx and tqx. Okay, so that is the topic of interest here. So the next thing that I want to discuss with you guys is the derivation of the definition of TPX and TQX. This has not been discussed in detail in the core reading of subject CD5, but it is in the core reading of subject CD4. but I think I should discuss it so that you can get a better understanding of the formulas given in the core reading of subject CD5 for these two quantities. They just state them directly and do not explain, but I am going to help you understand them right here. So the first thing we must know is a mathematical definition for mu x. I just told you that mu x is the probability that a life aged x dies in an infinitely small period, but I want to define it mathematically. So this is nothing but limit h tends to 0 hqx divided by h. What this definition here is saying is that the probability that a person dies in an infinitely small period of time is nothing but same as the probability that the person dies in a time period h, and you further divide this time period by h, and then you get such a small fraction of time where this person has to die. So that is the definition of mu x. To get a clearer look at this thing, we can write this in another form. If I take another limit h tending to 0, where h tends to 0, and I send this h on this side, on the other side, I can just write this as the probability that x dies in a small period h as nothing but h times mu x, h times the probability that it dies in an infinitely small period. And this is the way you can understand it, that mu x is so small that it is, if you want to find the probability that a person dies in a small period of time h, it is nothing but h times mu x. So this you can see as a unit, and I am just multiplying, I'm just adding up h units of mu x to get this. So that is something we learn in subject CD4, but it is required here, and this is the definition of mu x. The next thing I want to discuss with you is a derivation of the definition TPX. So if I want to derive the definition of TPX, I'm going to do it here. Again, a CD4 thing, but I'm going to do it for you guys. So the first thing we need to understand is a relation in TPX itself. It goes like T plus H PX is equal to TPX into HPX plus T. Okay, first of all, this might look really intimidating, but then if we try to understand this in detail, it is a very easy thing. If I try to think about what this is saying, is that the probability that a life aged x has to survive for another t plus h years, this is same as nothing but the probability that x survives for another t years into, that is, and these both things have to happen. We know that if we want to add up two events, two mutually exclusive events, we can just multiply them. So TPX, the probability that x survives for t years, and then this guy which has reached the age of x plus t survives for another h years. So the guy will reach at the age of x plus t plus h. If I try to understand this using a number line, I want to understand this using a number line here. So the guy is at the age x, and he wants to reach here the age x plus t plus h, x plus t plus h. So if he wants to go here, the way he can go is like this. Here is t plus h, this is t years, and this is h years. I'm sorry, this is x plus t, x, pardon my bad handwriting, I'm gonna write this right here. This is x plus t. So he was at x and he wants to reach x plus t plus h. So he can go directly, or he can go this way. He can first live for another t years from x to x plus t, and then he can live another h years from x plus t to x plus t plus h, which this definition is saying. So this is a fundamental thing we have discussed here, and this will be used throughout the entire subject CD5. And now I want to manipulate this to get a definition for TPX. So the way I will do this is that I will write this as something else. Just keep following my lead. T plus HPX is equal to, this implies that TPX into, this can be written as 1 minus HPX plus T. So as I told you, the sum of these two things is 1. So I am going to convert in a T probability into a Q probability. So this is what happens here. So I've taken this. Now the next thing I need to do is use the definition of this HQX plus T, which I had defined earlier. I will be using this definition for this quantity. So I can write this quantity as H into mu X plus T. Okay, so this is what I've got here, and then I'll put in the entire thing as it was. So I've got this, there was a TPX, and then there was a T plus HPX. Okay, this is it. Now the next thing we do is that I just open this bracket up. So this implies that T plus HPX is equals to TPX minus H times TPX into mu X plus T. Alright. Now the next thing that I do, and here some sort of magic will happen. You just have to remember that limit H tending to 0 was applicable here. Some sort of magic will happen. We will send this on the other side and this H in the denominator. So I can just write it as H plus TPX minus TPX, sending this in the denominator. H is equals to TPX into mu X plus T, and I know the limit H is tending to 0. If you look at this very carefully, you will see that this is nothing but the first principles of differential calculus. This is the definition of derivative of TPX. This is f of x plus h, this is fx, and this is divided by h. So I can just write this as the derivative of d by dt of TPX. Okay, and this is equal to nothing but this quantity TPX into mu x plus t. If I send this as a denominator on this side, then this would be 1 upon TPX into d by dt of TPX is equals to mu x plus t. Now finally, if I change this, if I want to change this, this would imply that this is nothing but the derivative of the log of TPX, because I've got a derivative of I've got a log derivative here, and then I've got a derivative of TPX and product. So I can just write it as d by dt of ln of TPX. Ln is of course the natural log and is equal to mu x plus t. If I integrate both the sides with respect to let's say I want to integrate these with respect to s. So if I want to take the integration of those two terms at both the sides, integrating both sides between the limits between t is equal to 0 and t is equal to s. So I'm just taking an integration. So integrating from 0 to s for the derivative of d by dt of log of tpx dt, and this was equal to the integral of, again taking an integral from 0 to s of mu x plus t. I'm sorry, this was negative. This was negative. I will change it in the previous slide too. Yeah. So this was a negative quantity here. I'll tell you how this was the minus sign. I forgot to put it here. So these are all negative quantities. Yeah. So this is a negative quantity, and yeah, this is how it works. So the next step would be that as I'm differentiating an integral, they'll just cancel out, and what I will get here would be the log of I'll put 0 in s in place of t minus log of 0 px, and this is equal to the negative integral from 0 to x s of mu x plus t dt. Okay, so this thing, this is the probability that x, the guy aged x, lives for another 0 years. That means that he lives for at least another 0 years. This would be 1 for obvious reasons, because he's not going to die immediately. Of course, no one dies like in a second. People do die in a second, but that won't be expected here. So this thing, it becomes 1 for obvious reasons, that this is just the probability that x dies in no time at all. 0 means no time at all. So this is 1, and the log of 1 is 0. So this entire thing, it becomes 0, and I'm just left with this, that is the log of spx, and this is equal to the integral from 0 to s negative of mu x plus t dt. Finally, taking both the sides to an exponential, so I'll just have the log and exponential will cancel, and spx would be equal to e to the power of negative integral of 0 to s mu x plus t dt, and this is the definition of pxs. In the core reading, this same definition, it is given in terms of t. So if I want the definition of probability that a person age x lives for another t years, that is nothing but e to the power of minus 0 to t mu. I cannot take take a t here, so I'll just take another variable. I'll take s ds. Okay, so this is your definition of tpx, and if you want to interpret it using your logic, this just says that this is the probability that a person dies in an infinitely small period of time, and I'm just adding these probabilities over the values from 0 to t. So this is the probability that he dies over this period of time, and as I'm taking a negative sign, this means that he does not die over a period of 0 to t years. And this is similar to the definition of force of interest. If I were to calculate a discounting factor from force of interest, this same definition would have applied. Okay. If I talk about the definition of TQX, that is nothing but 1 minus TPX. And there is one more definition of TQX given, and an equivalence between this definition and that definition can be proven, which I'll be doing later on. But that definition, I just want you to know it, that definition is that TQX is equal to the integral from 0 to t probability that a person is x lives for another s years and then dies in the very next second. So mu x plus s ds. So what this definition is saying intuitively, I want you to understand it. The derivation we might do later, but the intuitive proof is what is more important. This says that the probability that a person dies within the next t years is that the probability that he lives for s years and then he dies immediately at time x plus s, because this is the probability of dying in a second. So he lives for s years and he dies in the immediate next second, and this can happen over all the times. This can happen over all the times from 0 to t. There can be a lot of values of s, and for all these times I want to add the probability that the person dies. So that will give me the probability that the person dies within t years. So I'm just saying that he lives for s years and then he dies at the immediate moment, and I add this over all the possible values of t. And this definition helps us find out a lot of formulas of this subject CD5. So I want you to understand, I'm explaining it again. This means that the probability that a person aged x dies within t years, this is nothing but sum over all the values from 0 to t for the probability that the person lives for a period of s and then dies at the immediate moment s. So this is the probability that he dies at any point in this range, and that is what you need to understand. Subject CD5 is all about reading mathematics. That is what I keep telling people, that you need to read what you're writing. You need to understand what these symbols and everything mean and what I have written in the definition here. Intuitively you should understand it. So TQX is equal to the integration from 0 to t SPX into mu x plus s ds. Thank you. So the next thing that should naturally come to anyone's mind here is that we have learned about these quantities. We have just defined these quantities TPX and TQX and mu x and all of these. But the next thing that comes to us our mind is that how do we use these? How do we use these? And before that, what comes is how do we calculate them? So that is what I'm gonna discuss with you guys now, and the topic is called as empirical estimates, estimation of life probabilities. This is basically covered in chapter 3, life tables. Now what do I mean by this statement I've made here, this topic, the empirical estimation of life probabilities? You see, the thing is that these quantities, these survival and mortality probabilities, if I talk about them, any company would if I'm an insurer, I would need some sort of data to go on with and calculate these things, these quantities. If I want to calculate them, I need data, and the calculation of these quantities using data is referred to as empirical calculation of probabilities. So I would need data. Where do I get this data from? There is a tool called as life tables, which I can use to calculate these probabilities, and these life tables are summaries of the data, of the mortality data. How do we make these life tables is a subject of interest for subject CD4 again, because that is where we are told that how do we collect this data, what kind of data are taken, and how do we actually use them, and we graduate them into making a life table, how do we smoothen the curve and everything. That is all discussed in subject CD4. Our interest here is using these life tables in order to calculate the probabilities that I have mentioned above. So that is what I am going to do here. First of all, I will just to satisfy your curiosity, I would like to know that I would like to tell you that where do we get the data from. Basically, we get the data from various sources. There are sources like national censuses, which are conducted 10 years in most countries, and then there are past datas of life insurance companies. Life insurance companies maintain data of their past policies, their deaths and their survival and everything. So that is how we just get that data and we somehow make a life table, and you will get to know how do we do that in subject CD4. Here we will learn using a life table. So for first thing we need to know about life tables are a few notations that are used in a life table. So I'm gonna define the notations. Okay, so the first thing you need to know is a notation called as LX. This is basically, you can see it as it is not exactly the number of people alive of a particular age. It is not exactly this, but it is a representative figure of this. That means that the scale might be different, but it would in proportion represent the number of people alive at a particular age, and you can for all practical purposes see it like that. Okay, so with LX there is another notation that is called as L alpha. That is the number of people, again representative people, alive at the initial age in the life table. Initial age, that is where the life table begins from. Okay, so I just might for the purpose of this is called as the radix of the life table. The radix, RADIX. So for simplicity purposes, this is usually taken to be a representative figure like 10,000 or maybe 1 lakh. That is 100,000, or this is taken to be let's say a million, that is 10 lakhs, and so on. And such figures are taken as L alpha for the sake of simplicity. So if I want to represent a life table using LX, I can do it. Let's say I've got X, that is the age, and I am beginning this life table, I'm beginning the recording from the age of 20. This could have been 0, but here it is 20. So I have got 20, I've got 21, I've got 22, and I've got 23, and I've got, let's say I said 10,000 people were alive here, and then they let's say 20 people died. So okay, let's say 200 people died. So I've got 800 people here, and then 9,300 people here, and then I might just have 9,261 people here. So this is how people are dying, and this is what, these are very unrealistic figures, but yeah, this is what this shows. So this is how a life table is plotted. You can get a real example on page 68 of the tables. Page 68 shows ELT 15 males table. Okay, ELT 15 males. So you have got this table there, and you can check it out. And there is an example. LX is the radix is taken to be a million, that is 100,000 there, and then it has started at the age of 0, and if you are following the table, and then it reduces. Okay, so another symbol I would like to discuss with you guys now is dx. That is the symbol next to lx you must see on the table. That is the number of people that die in a year. Out of the ones that were alive. So that is what dx shows. So basically, if I talk about dx, so dx is nothing but lx minus lx plus 1. If you follow the ELT 15 table that I've been talking about, let's say when x is equal to 4, that is between ages 4 and 5, the number of people alive at age 4 were 99,056, and that at age 5 were 99,032. So the dx value here is obviously 24, right? That is the difference of these two figures, right? So this is cross verified. Okay, so now getting to how do I calculate TPX and TQX and all those figures out of these. So the definition for calculating TPX would obviously, as you would have expected, is LX plus T divided by LX. Okay, and if I want to calculate TQX, it would be 1 minus TPX, or I can write it as 1 minus let's say LX plus T upon LX, which would be equal to, if I take a LCM, then I would get LX minus LX plus T divided by LX. This not alright. So this is the definition. Okay. Okay. So the next thing I want to discuss are the definitions of PX and QX. That means this is the same as these things, but there is nothing written on this side, like there is no T here. So basically PX is same as writing PX1. That means if there is nothing written on this side, we assume it to be 1. Similarly, QX is equal to nothing but 1 QX. If I take an example of this, example of TPX can be 3p5. That would mean that the probability a boy aged 5 years lives for another 3 years. If I just write p5, if I write p5, that would mean that would be the same as 1p5. It is the same as 1p5. That is the probability that boy age 5 lives for at least another 1 year. So if I write nothing here, it's the same as this. Relating to this are their definitions. So obviously PX would be as you would expect, LX plus 1 upon LX, and QX is nothing but LX minus LX plus 1 divided by LX. That is, and LX minus LX plus 1 is obviously DX, so it is DX upon LX. Okay, so that is the definition. Now the last thing I want to discuss with you guys is the shape of the human mortality, which is another very important topic discussed here, and it is detailed in chapter number 14, the last chapter of the syllabus, but I am going to discuss it in brief here because it also forms a part of chapter number 3, life tables. So I would want to show you the curve of human mortality. To illustrate it, I have drawn a logarithmic QX curve. I've drawn this because if I would have drawn a normal QX curve as against age, as if I would have it would have only showed you like a rising line. The intricate details of the curve would have been missed. Log basically smoothens out the curve and helps us see only the major changes. So basically this is the shape of QX, and this is discussed in detail in the last chapter. So what we see here is that at birth the amount of deaths, the proportionate deaths QX are very high. This is referred to as infant mortality, that is, it is at birth. After that we see a fall in mortality as children are in a very protected environment. There are few deaths. After this the mortality falls, and this is low. At the, if I see this in detail, there is a rise in QX at the ages around 15 to 21. This is referred to as accidental hump. If you can see this hump right here, this hump, if you see this hump, this shows a rise in mortality between the ages of 15 to 21, because basically teenagers get out of their protected environment, and there are deaths due to accidents and drug abuse and a lot of things like that. So this is called as the accidental hump. After this there is a stable rise in the mortality, and it peaks at around 80 years of age, and the maximum human age is around, considered to be around 100 years. And that if I talk about a table, most of the tables, if we see ELT 15 table, this is plotted till the age of 109. The maximum human age is often denoted by the letter omega. It's written here, omega is equal to 100. So that is the maximum age in a table, and L omega is obviously equal to 0, because there is no one alive at this age. Everyone dies. Okay, so the maximum age is usually taken to be between 100 and 120, depending from table to table. Okay guys, so that was all for this video. Thank you, and I hope you enjoyed it, and I want to talk to you about a few things right now, very important things. As you know, this was the first part of my lecture 1, and there will be a second part, but I am sorry, I most probably won't be posting it on YouTube, and it would only come out on my Teachable portal, wherein you will have